Hey everyone. In this case, we're going to look at quadratic terms in linear regression models. So specifically, what we mean by that is we have one continuous dependent variable, y, and we have a continuous independent variable, x. And the key here is that we not only include x, but we also include a squared term for x, so x squared. And we have two parameters, beta 1 and beta 2, that is associated with the squared term, right? So in general, quadratic terms are used to capture decreasing or increasing marginal effects, right? So while we previously kind of looked at the slope for a continuous independent variable, where the 1 unit increase in x always, no matter where you are on kind of the range of x values, a 1 unit increase in x always had a constant effect on always led to it was always associated with the same change in your outcome variable y, or the expected change in the outcome variable y, right? And so as soon as that is not the case, and as soon as we have nonlinear effects, and particularly curvilinear effects, then these can be modeled using squared or quadratic terms, right? The important thing though to keep in mind is that these quadratic terms always kind of make interpretation slightly more difficult. The reason why it's more difficult is that now the effect of or the change in y that is associated with a 1 unit increase in x is now not constant across ranges of x, right? And we have to keep that in mind when we interpret those coefficients, okay? So as soon as we have this quadratic term included, beta 1 itself only measures the expected change in y for 1 unit increase in x at x equals 0, right? And so that's the important part when we interpret this kind of beta 1 coefficient. That basically tells us only something about the expected change in y that is associated with the 1 unit change in x at one specific value of x, namely x1 being equal to 0, right? And to kind of visualize this, I simulated some data. We have an intercept of 0.5, a x1 or beta 1 parameter of 0.9, and beta 2 here of minus 0.35, right? And so I plotted some data points as well as the kind of regression line that is described by this x1 and x1 square, the beta 1 and beta 2 parameter, right? And so so this is kind of the fitted line given beta 1 and beta 2, okay? The important part here is the beta 1 parameter is essentially the slope of the tangential line of this curve where x1 is equal to 0. And that sounds maybe too complicated, but essentially that describes exactly what I explained previously, which is this is the kind of instantaneous change for 1 unit increase in x1 at the point where x1 is equal to 0. So at that specific point on this curve, a 1 unit increase in x1 would result in a beta 1 increase in y, okay? Again, we're always talking about kind of associations and relationships, not necessarily, and those are not necessarily causal relationships, right? It's just statistical associations, right? So that's what the beta 1 parameter tells us, and kind of similar to the discussions in the previous videos about interactions and intercepts and kind of interpreting all the things that you interpret conditional on a specific variable being equal to 0 only has a sensible interpretation to the extent that that variable being equal to 0 actually has a sensible interpretation and actually is part of, you know, the range of values that you would usually observe, right? Again, going back to the example of GDP per capita as an independent variable, GDP per capita for countries is never 0, and so as soon as that's the case, the kind of slope or the effect of a 1 unit increase in GDP per capita for GDP per capita being equal to 0 is, of course, kind of not really informative for any of our substantive questions, because this is an extrapolation well beyond the range of sensible values that we're interested in, right? So imagine this. Sorry, there's my mouse. Imagine we fitted this line, but these values were all positive GDP per capita values, and x1 being equal to 0 would be all the way not even in the plot, but somewhere all the way to the left here. And so the slope, if we continue this line, the slope at that specific point would be extremely large, right? We would see an extremely large effect, but that effect doesn't really tell us anything, because that's just an extrapolation based on how this line would continue. Okay. So depending on how x1 is scaled, this beta 1 has a sensible interpretation, or it doesn't, depending on whether 0 is kind of in the range of possible values for our independent variable. Okay. The important thing, as I mentioned, is that this effect of x1, or the expected change that is associated with a 1 unit increase in x1, is not constant and changes, right? And so the next question is, how does it change across ranges of x, right? And so to answer that question, of course, what we have to do, or what we can do, is we can look at the first derivative of our regression of our model, because the first derivative, of course, the first derivative with respect to x, of course, tells us how the slope changes, so the rate of change changes over different values of x. Okay, so if we take the first derivative of this function, or this equation, with respect to x, of course what we're left with is beta 1 plus 2 times beta 2 x. Okay, so alpha drops out, this just becomes beta 1, this becomes 2 times beta 2 x. Okay, so this function now describes how the rate of change, or this kind of effect of x1 that I talked about for 1 unit increase in x, changes across different values of x. Okay, this is really helpful because it can also tell us, it can tell us two things. One, it can tell us, since this is kind of this quadratic term always models a curvilinear relationship that has that can be either U-shaped or reverse U-shaped, right? So reverse U-shaped like this, or U-shaped where it would go up like this. Okay, so just flipped around, right? And so if this is since this is the case, what we can do by calculating the first derivative, we can basically identify where the maximum and minimum of that curve is, and we can also tell whether it is a maximum or a minimum, right? So basically, just based by not even plotting this, but just by looking at these coefficients, we'll be able to say, one, whether this is U-shaped or reversed U-shaped by looking at the second derivative, and where exactly the maximum or the minimum of that U-shape is, right? So how do we find the maximum or minimum of that U-shape? We talked about this before in the math refresher and also in the OLS derivation part. Of course, we have to take the first derivative and set it equal to 0. Setting the first derivative equal to 0 is basically identifying the point where the tangential line has a slope of 0. So that means identifying this critical point up here. Okay. So if we take this function and we set this equal to 0 and then solve for x, what we're going to get is, of course, we can put this beta 1 on the other side and divide by 2 times beta 2. And that means solving for x, we get this equation x star, that's our kind of critical point, is minus beta 1 divided by 2 times beta 2. Right? So whenever you have a quadratic term and you're interested and you know this quadratic term implies that there is a curvilinear relationship that's either U-shaped or reverse U-shaped. The first thing is you can compute minus beta 1 divided by 2 times beta 2. So in our case, that would be minus 0.94 divided by 2 times minus 0.3459 and so on. And that gives you the critical point, basically, that is either a minimum or a maximum in the curve that was fit through that line, right? So if you now take your calculator and compute minus beta 1 divided by 2 times beta 2, you'll see that the result is something around 1.3, right? So minus beta 1 divided by 2 times beta 2 is basically just the distance here between 0 and on the x1 axis, on the x-axis, between those 2 points. Okay, so x star is something around 1.3. That means the minimum or maximum is at this specific point, right? So we know it's curvilinear, we know it's either U-shaped or reverse U-shaped, and we know the minima or maxima is right here. The next thing is to see whether this point is actually a minimum or a maximum, which determines whether this is U-shaped or reverse U-shaped. And of course, kind of going back to our calculus, in order to identify this, we need to take the second derivative at that point, x star. The second derivative is of course the derivative of this equation with respect to x again, and of course beta 1 drops out, and what we're left with is 2 times beta 2, right? And so the nice thing here is that 2 times beta 2, we can directly see this this is positive for beta 2 being positive and negative for beta 2 being negative, right? Just because this is not a function of x anymore, this is just beta 2, right? Whenever the second derivative is negative, that means the function itself is concave, and if the function itself, or if the function is concave, that means this is a this must be a maximum, right? So second derivative, we look at beta 2. If beta 2 is negative, we know this is concave, and we know that this must be a maximum. If beta 2 is positive, then the second derivative is positive. If the second derivative is positive, that means the function is convex. That means the critical point that we identified previously is a minimum. So by looking at this x square, we can directly tell, is it U-shaped or is it a reverse U-shaped? If it's negative, then it's reverse U-shaped. If beta 2 is positive, then it's U-shaped, okay? Here it's negative, so it's reverse U-shaped. The critical point is a maximum. In addition, it's always useful to identify this critical point because, again, remember that we're kind of modeling a potentially U-shaped or reverse U-shaped relationship, but it could be the case, it could very well be the case that the critical point that we identify is actually outside of the range of reasonable values of x that we actually observe, right? So as soon as that is the case, then what we're fitting is not actually really a U-shaped or reverse U-shaped relationship, because in the kind of within the range of x values that we observe, the reversal of the relationship being going from positive to negative, for example, doesn't really it's not included in those x values, right? So in other words, you could think of imagine we kind of fit a curve through these observations, and rather than having the maximum here, we would have the maximum, all the way, outside of the screen right here, and the relevant portion where we actually observe points is actually kind of a line that is still continuously increasing. It is, it has a decreasing slope, but it doesn't reach the point where the slope actually turns negative, right? And so you kind of want to be aware, if you fit a regression with a quadratic term, you want to know, is this really, and you see, okay, this is negative, so this must be a reverse U-shaped relationship, right? So if in order to be careful, you want to know what is the actual critical point. Is that critical point actually within the range of x values that we observe, in order to be sure to say, okay, this is actually truly a reverse U-shaped relationship, because otherwise it would just be a relationship with decreasing marginal effects, but it's not really U-shaped or reverse U-shaped in that sense, because the slope never flips, at least in the range of data, or in the range or across the range of axes that we actually observe. Okay, so as we see, quadratic terms are extremely useful, but they make interpretation of those individual coefficients a lot more challenging, a lot more difficult, and so plotting those and kind of visualizing what is going on is often extremely helpful. All right, in the next one, let's see, where are we? In the next one, we're going to talk about natural logarithms.